All right, hey guys, this is our first video of our first chapter and our first section. You might notice that your notes look very similar to my notes, so you should be able to follow along, filling in the blanks and going over the examples as we go through them together, just like if we were in class. Now, you might need to pause the video at some points. You might need to rewind and rewatch some of the videos at certain points. I know sometimes I do tend to talk a little bit quickly. I apologize, it's kind of a bad habit, but that's one nice thing about having these videos is that you can pause, you can go back and replay, you can listen to it as many times as you need to make sure that you understand, okay? All right, we're going to go ahead and start into limits. This is section 11.1 in our first chapter. Chapter 11. There's a lot of information actually in this section. It's going to take a little bit of time to get through all of it, but this section is really important because it lays the foundation for almost every other thing we do in calculus, okay? I kind of started off with kind of an application example of where you might see a limit problem in real life. I think I'm probably going to skip that for now, but you're welcome to look over that and look at the answers there to kind of see how you would see a limit in an application problem. But let's go ahead and get right into it and talk about what a limit is. So my informal definition of a limit. The limit of a function, f of x, describes the behavior of that function close to a particular x value. It doesn't necessarily give you the value right there, it just tells you what's happening as you get close to that x value. So we're not really looking for the function value, let's say when x equals 3. We're looking to see what happens on our function as we approach 3. So like if you were following the path, if I was coming from the left side and you were coming from the right side, where would we be together? Okay, there's a couple of different notations for limits. We have the limit as x approaches c of f of x equals a certain value. Some books use c, some books use a. They're just saying that we're approaching a certain value on the x. So the limit as x approaches a of f of x equals a certain number L. You notice that we have to have all of those parts. We need to have a function, whether you call it f of x or whether you actually put the equation in there, so we know what we're finding the limit of. Okay? So let me give you an example with this picture off to the left. I'm going to put in numbers. I put in a 3 on my x and a 5 on my y. If I was looking at the actual function value, you notice that there's a hole in my graph, right? And so if I was looking for f of 3, when x is 3, what is my y value? You notice that there is no y value there because there's an open circle and no other dot on x equals 3. And so f of 3 does not exist. There is no value at x equals 3. But a limit question is a little bit different. When I ask you for the limit as x approaches 3 of f of x, I'm not looking for what's happening at 3, I'm looking for what's happening as we follow this path and get close to 3 on both sides. There might not be anything there, but we can get really close together if you were following the path from the left and I was following the path from the right, right? So an analogy, kind of silly, but I use it in my classes, is that if I wanted to meet you at Starbucks, as we approach Starbucks might not be open yet, but we can still be together and wait outside until they open. So we would say on this one, the limit as x approaches 3, as we approach 3, what is our y value? Well, our y value is 5. So the limit as x approaches 3 of f of x is 5. Even though there might not be a number at x equals 3, we can get really close to it and be there together at y equals 5. So you notice that limits are actually y values. We can approach a certain x value, and then what is our y value as we approach that x value? So again, the function does not have to be defined at that value in order to have a limit as we approach that value. So just like our picture, just because there's a hole doesn't mean that our limit doesn't exist. We just have to follow the path and get close to it. And if we're together at 5, then that's what our limit is. If a function does not approach the same number, though, from the left side to the right side, then we say that the limit doesn't exist. So if I had a graph and I was coming up to the graph here, let's say my graph looked something like this. Okay, and so if I was approaching my graph from the left of 3, I'd be up here. If you were approaching to the right of 3, you'd be down here. And you notice there's a big old gap in between those two? That would mean that our limit doesn't exist. So if you're following and if it doesn't approach the same number from the left side and the right side, then we say that our limit doesn't exist, or we use the abbreviation DNE for does not exist. Now, up here, our limit did exist. Even though there was a hole, when we followed the path, we could meet together at 5. Even though Starbucks was closed, we can wait out front until they open. On this picture, you were over at Starbucks and I was across the street at QT. And because we're not together, our limit doesn't exist. So if there's a big old gap, as x approaches 3, then our limit does not exist. So that's one example of when a limit may not exist. We can evaluate limits a couple different ways. We're going to talk about 3 of them. The first way is doing a table of values. We can punch in numbers really close to 3 on both sides. We can do 2, 2.5, 2.8, 2.9, 2.999, and get really close to 3 from the left and see what happens on our y value. We can also plug in numbers really close to 3 on the other side. We can do 4, we can do 3.5, we can do 3.3, we could do 3.1, we could do 3.01. We can get really close to 3 on both sides and see what happens with our outputs, our y values. If they end up looking like they both approach 5, well then our limit is going to be 5. If one approaches 5 and the other one approaches -12, well we know we're not going to be together and our limit wouldn't exist. So doing a table of values, plugging in numbers and seeing what happens as we approach a certain x value. The second way is graphically. If I give you a picture, just kind of like I did up here, can we look at that picture? Can we follow the path and see what happens as we approach x equals 3? Okay, so looking at a picture would be a graphical approach. And the last way is algebraically. Can we actually use some algebra? Can we evaluate by substituting, by factoring, by actually doing some math to figure out what the limit is? We're going to talk quickly about those 3 ways. The 2 ways we're going to use the most are probably graphically and algebraically, but we will do a quick example on a table of values. We just don't use that technique as often because it's not as efficient. You can imagine we're plugging and chugging and plugging and chugging and plugging and chugging and plugging in a whole bunch of numbers, and it takes a while. But we will do an example of all 3. Let's quickly do an example of a graphing approach, and then I'll have you try some problems. So again, a graphic approach has you looking at a graph and seeing what happens as you approach a certain x value. So look at these 3 pictures. They've given you A's and L's for X's and Y's, but I'm going to go ahead and change those so I can actually put a value to it. Why don't you go ahead and change it so that instead of saying A, it says 5, and instead of saying L, it says 7. So that way we can put some actual numbers on it. If you're looking at this first graph, as we're following the path, if we're following the path and we want to approach 5, I'm coming from the left, so I'm following the path this way. You're coming from the right, so you're following the path this way. What happens when we approach 5? Well, we're up there together, aren't we? We're up there together at y equals 7. So I would say on this graph that the limit as x approaches 5 of f of x is 7. As we follow the path, we're going to end up together at y equals 7. You might also notice that there is a function value. There's a dot right here. So if I asked you what is f of 5, if you were to plug in 5 for x, what would you get out as your y value? Well, you would get out a 7 because there is a dot there. So my function value and my limit happen to be the same. But look at the middle graph. That middle graph looks a little bit different than the first one. If you look carefully, you may notice that there's an actual hole in the graph right there. There's a dot down here, but there's a hole on my function on that path. So if I asked you for f of 5, if you plug in 5 for x, what value do you get out on the y? Well, you get out a 4 because that's where the dot is. If I plug in a 5, I get out a 4. My function value has a value of 4. But if I change the question and I ask you now for the limit as x approaches 5, remember doing a limit means we're following the path. So if I'm following the path from the left and I approach 5, and you're following the path from the right and you approach 5, are we going to be together? Yeah, and remember, even though Starbucks is closed, we can still hang out together until they open. And where are we? Well, we're up there at 7. So even though there was a hole, we could follow the path, and we can say that the limit as x approaches 5 of f of x is 7. Even though there might be a QT that's across the street and it's open, we want to be up here on the path. So even though there's a hole, we can still have a limit. And they might not be the same value. The function value and the limit value might be a little bit different. Okay, look at the last graph. The last graph also has a hole right there, and it has no other dot. So if I asked you for the function value, f of 5, if I plugged in a 5 for x, what y value would we get? Well, you notice that there is no y value. There's no dot along the y at x equals 5. So my function value doesn't exist. But does my limit exist? Well, remember, as soon as you see that word limit, think of following the path. I want to follow the path from the left, you want to follow the path from the right, and I want to know if we're going to be together. And even though there's a hole, doesn't mean we can't be together. Even though Starbucks is closed, doesn't mean we can't hang out until they open. So what would you say the limit is here? It should also be 7. So you notice that on all 3 of these graphs, they might look a little bit different. However, their limit is still the same. We still all have a path that approaches, as x approaches 5, we end up there at 7 on all 3 of them, even though one has a hole, even though one has a hole but a dot, and even though one has no hole and just a solid path. Okay, so 3 different cases where the limit is still 7. Let's do one more example, and then I'll have you look at some other types of limit questions. Let's look at example 1. So example number 1 has 4 different pictures. It's going to ask you for a limit as x approaches 3 on each of these, and I'm also going to ask you for the function value, f of 3. That way we can kind of compare. Maybe you can pause the video and try these 4 first on your own to see if you're really understanding. So pause the video and see if you get the same answer as I do. All right, looking at example number 1a, the limit as we approach 3. So I'm approaching from the left, you're approaching from the right. It looks like we're going to be together right there at 2. Since there is a dot at 2, f of 3 is also 2. So the answers end up being the same. Look at b though. F of 3 does not exist. There is no y value because there's an open circle and nothing else there when x is 3. But what is the limit as x approaches 3? So I'm thinking following the path. If I'm following the path from the left and you're following the path from the right, aren't we going to be together even though Starbucks is closed? So even though there's a hole there, we can still meet up together at y equals 2. So my limit is 2, but my function value doesn't exist. A little bit different. All right, what about C? What is my function value? If you were to plug in 3 for x, would you get out a y value? Well, it looks like on this one, there is a dot up there at 3. So f of 3 is 3. But what is the limit as x approaches 3? Now we have to think about being on the path. If we're on the path and we're approaching from both directions, it looks like we're going to still end up together. Even though Starbucks is closed, we can meet up together at 2. So the limit as x approaches 3 is 2. Even though there might be a dot somewhere else, we don't care about that if we're talking about the limit. We care about following the function or the path. All right, the last one, D. F of 3 is 3. That's where my dot is. What is the limit, though, as we approach 3? Well, if I'm following the path from the left and you're following the path from the right, are we going to be together? Well, you notice that there's a big old gap. We're not together. You're across the street. And so I would say on this one that the limit as x approaches 3 of f of x does not exist because we're not together. There's a big old gap in our path. It's okay to have a hole. The limit might still exist. But if there's a big old gap, then we're definitely not together and the limit doesn't exist. Make sure you can look at a graph and determine not only function value, but the limit as x approaches a certain value.